Hello everyone, welcome, and today we're going to be looking at enthalpy change in AS level chemistry. So, let's first learn what is enthalpy. Enthalpy is basically just a measure of the total chemical energy inside of a substance or a molecule, and it's represented by delta H, and we will be positive or negative depending on the type of reaction, which we'll be looking at later on. The first type of reaction we're going to be learning about are exothermic reactions. So a exothermic reaction occurs when the products of a reaction have less energy than the reactants. So basically, the energy is being lost by the products, so it's being given off to the surroundings near them. And this will mean the enthalpy has decreased because the total chemical energy in the products has decreased, so the change in enthalpy, delta H, will be negative. Now, let's just look at endothermic reactions. So these are the opposite of exothermic. So this is when the products have more energy than the reactants. So that means energy is being taken in from the surroundings. Heat is being taken in from the surroundings. And this will cause a delta positive enthalpy change, as that's obvious. And let's look at how you draw these enthalpy changes. So we're drawing them using a reaction pathway diagram. And it basically shows us the energies of the reactants, the transition state, which I'll talk about later, and the product of the reaction as the reaction progresses. So the transition state in a reaction pathway diagram, which we'll see later on, is just the area where the bonds are being partially broken and new bonds are being formed. And the activation energy is basically the amount of energy you need to reach that transition state. So if we look at this example over here, in an endothermic reaction, where the products have more energy than the reactants, so the energy of the reactants must be lower than the product, as it's a higher energy. And the activation energy is the amount of energy needed to start that reaction, which we'll look into later how to find it. And over here, this area, this humped area, this is where there's a transition state. This is where the bonds are being broken and new bonds are being made. And similarly, in an exothermic reaction, we know this is the activation energy. This is the energy release. This is the delta H, and over here, this will be the delta H, which will be positive. This will be negative. And over here, we can see the reactants have more energy than the products, as energy is being given off. Now, let us look at how you measure enthalpy change. So there's some conditions which must be obeyed when we're doing enthalpy change, but you must have a pressure of 101,000 kilopascals. It must be 25 degrees or 298 kelvins, and each substance must be in its normal physical state at room temperature. So at water, it must be a liquid, oxygen, it would be a gas. So there's 4 standards of enthalpy changes we're looking at. We'll be first looking at the reaction, which is denoted by delta H. This symbol is basically used to represent that it's a constant temperature. It's at the optimal temperature, which are these, and R, which just shows this reaction. And this is basically when the measure of the enthalpy change of an equation where the products are formed, and it can be endothermic or exothermic. Next is formation, which is represented by delta HF, and this is basically a measure of the enthalpy change, which is of like the amount released when 1 mole of a compound is formed from its elements. So there's only one product being formed, and again it can be exothermic or endothermic. Next is combustion, and it's basically the measure of the enthalpy change when 1 mole of substance is burned in excess oxygen. And this will have to be exothermic, and this is because if we burn something, obviously heat is being given off. That is why it's an exothermic reaction. And similarly, neutralization, which is just a measure of the energy change when 1 mole of water is formed from reacted an acid with an alkali. And this will obviously also be an exothermic reaction. So let's just look at how you measure enthalpy change. So this is done by using a calorimeter, which is made up of a plastic lid, a polystyrene cup, the mixture, and a thermometer. So basically, we need to use a plastic lid and polystyrene to avoid heat being lost to other factors to the environment to get the most accurate possible value. So how you measure enthalpy change is you surround this apparatus. So you have actually like a cup in here, and you surround this by water, and the reaction mixture will be in here, and you will measure the temperature. You actually measure the temperature of the water, and there's a specific formula we use, which is called specific heat capacity. So the amount of energy released is mass of the water times the specific heat capacity, which always in the case of water is 4.18, and then times the change in temperature. So whenever 1 gram of water is heated by 1 degree, it requires 4.18 joules of energy. So if we do this reaction and we can measure the change in the temperature of the water, we can then find the amount of energy that was released by this mixture, or the amount taken in by the mixture, and we can just find the per mole enthalpy by just finding the moles of the product. In the transition state, some bonds are being broken and new bonds are being made. So bond breaking, if you imagine I have hydrogen and a hydrogen, I'll have to put in some sort of some amount of energy to break this bond, to disassociate them. So that would be the amount of energy. That would be an endothermic reaction because I'm taking in heat. And as conversely, when I'm forming a bond, a new bond is being formed between the hydrogens, I'm releasing energy. And this is very important to calculating the enthalpy changes. So let us know what is exact enthalpy bond energy. Let us know what is exact bond energy. So the exact bond energy is the amount of energy required to break 1 mole of a specific covalent bond in its gas phase. Remember, this is important. In a gas phase, it is called the bond dissociation energy, or exact bond energy. So imagine I have O and H, and if I have 1 mole of this, and the amount of energy required to break 1 mole of it will be the exact bond energy. However, this isn't always accurate, which is where we learn about average bond energy, because the bond energy can be influenced by other atoms in this molecules. Therefore, an average of the number of the same type of bonds but in different environment is calculated. So let us take the example of water and ethanol. We know water is OH, right? And what do we know about ethanol? It's CH3, COH, and we have hydrogen here and hydrogen here, right? So obviously the amount of energy to break this OH will be very different to the amount of energy to break this OH, because this is attached to a carbon or this is attached to oxygen, so we take more energy to break the oxygen one. Okay, so the average amount of bond energy, the average amount of energy to break this bond and countless others, that would give us the average bond energy, which we use in our calculations. So let us do some examples to learn about this better. So the question over here says, an experiment was carried out to determine the approximate value of the molar enthalpy change of neutralization. Well, we already know neutralization has a negative energy, so we can see all these are negative energy, so we know none of them is automatically wrong. So 75 centimeters of 3 mole of hydrochloric acid was placed in a polystyrene beaker with negligible heat capacity. Its temperature was recorded, and then 75 centimeters cubed of 3 moles of potassium hydroxide is added to the same temperature and is stirred. The temperature rose by 14 degrees. The resulting solution may be considered to have a specific heat capacity of 4.18. So, as you know, we need to consider what is the formula to find the enthalpy change. First, we need to find the change in energy. Is Q equals to M times C times delta T. What is C? C is 4.18 as given, and the change in temperature is 14 degrees. We don't have to worry about making it to kelvins. And now the mass. The mass of the substance can be taken as a total volume of the mixtures, of the two things that are being mixed. It's not about the water. We measure it based on the 1 mole of water, but it's actually the mass of the substances. So just this case is 150 centimeters, and we just take 1 centimeter as 1 gram, so we can take it as 150. So with that, we can calculate the energy, which will be 150 times 4.18 times 14, which is about 8,778. Now, to find the enthalpy, it's the change in energy over the moles. And how do you find the moles? Since there's an equal number, if you write the equation, it's a 1-to-1 ratio. We need to find the moles of this. Let's take the hydrochloric acid, which would just be 75 over 1,000 times 3, 0.225. So we can calculate the energy, which is 8,778 divided by that, which will give us 39,013 joules per mole, or option B. Now let's just move on to the next question. The compound R is turned into compound T without reaction, and then turned into compound S, which can be acylated. This gives us the steps involved. So we can see R2S is positive, so this is an endothermic reaction. So the energy of the reactants and the product should be over here. So if we over here know that going from S to T is delta negative, so we would have to go the products over here. It would have a lower reactant, so it'll be below. So which type of reaction would this be? It cannot be B because that only shows one. That's a transition state. Same for C. And D is incorrect because it's going lower. So this will be a negative. So hence this is option A. Now let's move on to the next question. This is the type of questions you'd expect in bond energies. So in a gas state, phosphorus pentachloride can be thermally decomposed to gaseous phosphorus trichloride and chlorine. We can see over here. The table gives the relevant bond energies found in these compounds. What is the enthalpy change of decomposition of this reaction? So let us see. We have over here PCl5. What can this be written as? This can just be written as PCl, but there's 5 of these bonds, correct? And when we're making new things, we're breaking down all the bonds and forming new bonds. So how much energy would we have to supply to break these 5 PCl bonds? So you know PCl is 328. So 328 times 5, it will be 1640. So 1640 will be the endothermic amount of energy we need. And over here we can see PCl3. So we have 3 PCLs and then we have 1 Cl. So we need to calculate the energies of that. So 3 PCLs will be simply 328 times 3 or 984, and 1 ClCl will just be 241. So if we add these up, we will get the total energy to make these ones. So the released energy is 1225. And the formula, so we're taking in more energies than compared to what we're releasing. So it would just be 1640 minus 1225. So we'll be taking in a net of 415 kilojoules. So it'll be option B. Now let us look at another question. Which equation correctly shows the bond energies for the covalent bond Y to Z can be calculated by dividing delta H by M? So look, how do we calculate bond energy? This is a very good question. If, for imagine, I have the compound YZ, right? We have in this equation, and I have, let's say, YZ5, where N is the number of covalent bonds, right? That is the value by N. So if I broke this, if I broke this and decomposed this, I would simply get Y and then Z, right? And the amount of energy to break one bond of this can we just consider as Y by Z, the bond, divided by N, correct? So if we imagine that, this will be represented by the equation D. Yeah, so this equation will be represented by option D because we want there to be no products formed. Because if a product forms, then obviously it would be incorrect because then there will be some sort of energy which will be released when making the bonds. So it cannot be that. So it cannot be any of the ones which have products, so B or C, and it will be YZN. Because if you imagine this, if I have CH4, right? If I want to find the energy to break down one bond of this, it will be CHHH, right? And if I formed C plus 4H, and if I just divided the total energy of this, which is just breaking these 4 bonds, divided by 4, we'll get the average energy of breaking this bond, which is YZ. Hence, this is option D. Now let's look at the final question. The diagram shows the skeletal formula of cyclobutane. The enthalpy change of the formulation of cyclobutane is 75.1 kilojoules per mole. The enthalpy change of the atomization of graphite is 712 kilojoules per mole. The bond enthalpy of CH1 is 390 kilojoules and HH is 429. So let's see. What is the formula to make cyclobutane? It is C plus 4H2. It is C plus 4H2, which will give us, 4 C's. This will give us C4H8. This is the formula of cyclobutane. So, what is the amount of energy to atomization of carbon, which is the graphite which we're using? So, this will be 4 times 712. So 4 times 712. That is the amount of energy for that. plus the amount of energy for height, the HH1 we know is 429, so that would be 429 times 4, right? So the total amount of energy we would need, so the endothermic amount can be found using this. So that would be 4 times 712, and then add that with 429 times 4, which will be 4,564, right? And we know minus some amount of energy to make this molecule will give us a net total of 75, right? 75.1. So the amount of energy that is released by these molecules is, we can take as 4489, rounded up, right? And then let us draw the diagram of cyclobutane. Let us draw the diagram. So we have C, 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 C. So there'll be a H bond here, there's a H bond here, there's a H bond here, and there's a H bond here, so on, so forth. So we know this is a diagram of cyclobutane, right? And we're breaking 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. So we need to subtract that from this value, right? So that would be 3, so 4488.9, which was the actual value. And we'll subtract that from 8 times 390, which will give us 1369 as a total, rounded up. And if we just divide that by 4, because there's 4 bonds, this will give us 342. So the answer here would be C. And thank you everyone for watching. I wish you guys the best of luck for your exams.